Hello, and thank you for coming to our presentation titled Stability and Performance Improvement with Feedback in Vrm Transconductance Error Amplifiers, a case study using the Sandler state space average Vrm model. My name is Ben Dannan, and I'll be presenting this EDI-Con presentation today. This presentation was done in collaboration with Steve Sandler and Heidi Barnes. As an overview, we're going to start by discussing why do we care about the transconductance inside the error amplifier of our VRMs, go into some background on transconductance amplifiers, then follow up with feedback loop basics and some control theory, and then move into our case study, which is broken in two parts. From there, we're going to summary and conclusions and close with questions. So why do we care about the transconductance tolerance of our error amplifier inside of our VRMs? Well, let's look at an example. Here we're showing an ADI ADP 2389 VRM. We're showing it with two different compensation networks, and we're showing the step response based on those two compensation networks. The left plot is the VRM step response when the transconductance of the error amplifier is at the datasheet minimum at 450 microsiemens. The right plot is the step response for the same evaluation VRM when the transconductance of the error amplifier is at the datasheet nominal value of 500 microsiemens. In each of the plots, the blue curve represents a shunt compensation network, whereas the red curve in both plots represents a series compensation network. What's important to note is as you look at the difference in the values in the overall transient response of the two blue curves, you see over 10 millivolts difference. And that's due to the tolerance of the transconductance error amplifier versus when comparing the two transient responses from the two red curves in each of the plots, you see less than a fraction of a millivolt. Now this is important, right? Because here what we're showing you from the data sheet is this ADI VRM only has around a 10% variation in the transconductance. However, there are multiple VRMs that have 30% or even worse variation in the error amplifier's transconductance. The takeaway here is that the tolerance of the transconductance error amplifier inside the VRM greatly impacts the transient response of your design. I don't think designers really want to suffer like this. Do you? So let's talk about how to improve your design without adding cost. First, let's quickly cover what makes up a VRM, more specifically a buck regulator. A VRM is typically comprised of logic drivers, switches, PWM comparators with a slope compensation, and an error amplifier. The loop gain of the VRM system is defined as the product of the transfer function along the closed control loop. Here we can see there are three products that create the overall transfer function. The takeaway here is that the error amplifier feedback loop affects the output impedance of the VRM. However, the transconductance of the error amplifier has a manufacturing tolerance, which we stated earlier, that can vary by over 30%. This can affect the output impedance and also the transient response of your VRM. So, before we can understand how to mitigate the sensitivity of the transconductance in the error amplifier inside our VRM, let's discuss what is a transconductance amplifier. Well, a transconductance amplifier is a voltage to current converter that makes it easy to electronically control the voltage feedback signals from DC to a bandwidth in the multiples of megahertz. In a buck controller, the transconductance amplifier is usually known as the error amplifier. These amplifiers are used since they have really wide bandwidths and they're also really cheap feedback amplifiers. The error amplifier plays an important role in power integrity optimization strategies. Manufacturers typically recommend the shunt termination of this transconductance amplifier, which is shown in the left plot. However, as we just showed, this is not going to give you the best transient response. What we will show today is that by using a series termination or shunt compensation, as shown in the right plot, you can better optimize your VRM for power integrity to match to the target impedance of your load, such as an ASIC or an FPGA. Negative feedback with amplifiers is not a new concept. In fact, we can go through the math here to show how to derive the closed loop gain of an amplifier. In this case, where alpha represents the transconductance of the amplifier, and our closed loop gain is defined by alpha multiplied by beta. From that, we can see that the desensitivity factor is really what's in the denominator of our closed loop gain, which is 1 plus alpha times beta. By differentiating our closed loop gain with respect to alpha and rearranging terms, we can see that the large loop gain, even a substantial change in alpha, will cause an insignificant change in our closed loop gain. This proves how negative feedback desensitizes gain. Going a step further, we can determine amplifier gain for both the shunt and the series compensation networks, which is really a transfer function of Vcomp over Vout. Now, by taking the derivative of the amplifier gain with respect to transconductance, we can compare the two results and conclude that the sensitivity of the series termination amplifier gain to transconductance is lower than that of the shunt termination. This sensitivity directly translates to the sensitivity of the closed loop functions of PSRR and output impedance. Therefore, series termination is a better solution. Now, to prove what we just said, let's look at our case study results across 5 VRMs from 4 different manufacturers. That includes ADI, Intercell, Texas Instruments, and Maxim. In this first part of this case study, we will show the differences in gain sensitivity and nonlinear distortion reduction by using a shunt and comparing it to a series compensation network. To start with case 1, we are looking again at the ADI ADP 2389 VRM. In this example, the datasheet tells us what the transconductance is, as well as the variation, which we can see is around 10% from nominal. Based on the 2 amplifier circuits shown, we can ensure that the nominal gain for the 2 compensation networks, being shunt and series, is set to the same at 1.67. As you can see by the left plot, both compensation networks have the same nominal gain as we calculated before. However, as we see in the middle plot, by sweeping the air amplifier's transconductance from the datasheet values at 450 microsiemens, 500 microsiemens, and a 550 microsiemens, we can see a wider range of output voltages from Vcomp when using the shunt compensation versus when Vcomp output is based off a series compensation. Here, with the series compensation, we see a much tighter variation or much narrower output for Vcomp. Further, when we plot Vcomp output versus the air amplifier's transconductance range, we can show much less sensitivity with the series feedback network versus the shunt compensation. So this validates our math shown earlier and proves that the series feedback is less sensitive to gain variation while exhibiting less linear distortion. So let's move to case 2. Case 2 is with the ISL 8026 VRM from Intercell. We can see that there is not an air amplifier transconductance variation given from the manufacturer datasheet. In fact, we only see a nominal value is provided at 120 microsiemens. As mentioned earlier, even though the VRM can have sensitivity to this number, and transconductance is a huge performance factor, most VRM datasheets do not provide the tolerance for transconductance. So how would you design for it? The answer is you can't. So in this example, let's assume a plus or minus 50% variation to assess sensitivity and linear distortion. This puts our minimum at around 60 microsiemens and our maximum at 180 microsiemens. Here again, we can calculate the same nominal gain for the two compensation networks based on the nominal transconductance value, which is set to a gain of 4. Again, by referencing the middle plot, we see a much larger variation in the Vcomp output with the shunt compensation versus when using the series compensation. By referencing the plot on the right, we see the series compensation network allows Vcomp again to be less sensitive to gain variation of the amplifier. In fact, you will notice that the next 3 VRM cases will show the same results as we've shown here with the first 2 cases. So for case 3, we're going to look at the Texas Instruments LM20143 VRM. Again, we're calculating the gain to be 3.38 based on the nominal transconductance value of 510 microsiemens. As you can see, we get the same results as shown by the previous 2 test cases. So let's move on. Moving on to test case 4, we're going to look at a space grade part, a radiation tolerant VRM from TI, the TPS 7H4003, which is designed for LEO and GEO space applications. I'm going to tell you right now, the results are not going to surprise you. Here we go. As shown here, the results for the space grade part do not change at all from what we showed previously in the earlier examples. In fact, we still see less linear distortion and better gain desensitivity by using the series feedback compensation network. Now let's move on to the last test case case 5. This is a part from Maxim, the Max 298 VRM. Here we can see the datasheet actually does provide us the variation from nominal, and we see it varies down to minus 44% and varies up to plus 50% from nominal. This is a huge variation, and this means designers will see the impact of this transconductance variation in the transient response, and you cannot mitigate this by using the shunt compensation network. Again, as we've shown in the earlier 4 test cases, the results here are no different. We can see that Vcomp output when comparing the shunt versus the series compensation is much wider with the shunt compensation, and we have a tighter output range with the series. So now let's move on to the second part of our case study, where we compare the same 5 VRMs and look at the impact on stability, the VRM's output impedance, and in some cases, the transient response. All the analysis shown here is based off building complete state space average models in Keysight ADS. Each of the VRM models that was built and shown in ADS here was done after characterizing the VRM on a VRM eval board after doing multiple measurements. At the end of this presentation, there are depictions of all the Sandler state space average models for everyone to reference. When looking at test case 1 with the ADP 2389, we see the left plot shows the output impedance results using the ADI design currently on the evaluation board. That's represented by the blue curve. The red curve in the left plot is the result of the VRM output impedance by removing the shunt compensation network and adding a series compensation network using a single 2.3 mega ohm series feedback resistor between Vcomp and the VRM's feedback pins, in addition to adjusting some of the output capacitor values. Now notice, the VRM's output impedance is now completely flat. VRM manufacturers use transient response as a figure of merit. Okay, so in this case, let's look at the ADP 2389, which is rated to deliver 12 amps continuously. Looking at the impedance plot, we see with the shunt compensation output impedance, we have a peak of around 18 milliohms at 50 kilohertz. At the same point in frequency with the series compensation network, it's around 1 milliohm. So if we want to think about this from a transient response, if we put a 1 amp step into this network, we should see 18 millivolts of ripple with the shunt compensation network output impedance and 1 millivolt of ripple with the series compensation network impedance result. Now, if we scale that to 10 amps and we can move our eyes over to the right plot, we can see the actual results here, and we see 95 millivolts of ripple based on a 20 microsecond step edge and a 10 amp step versus 10 millivolts of output transient response with the series compensation. Here we can clearly show that by designing your VRM's output impedance to be completely flat, there is an 89% improvement in the transient response. The takeaway is that the VRM transconductance tolerance greatly varies the transient response of your design. Remember, as we showed previously, by using a series compensation design, we are less sensitive to the gain variation of the amplifier. Here we have the output impedance result for the same VRM, and we're looking at it using non-invasive stability measurement, or NISM. NISM can be used to determine the phase margin or stability margin from an output impedance simulation in ADS. NISM can also be used on almost all the VNAs today when measuring output impedance. From NISM, we see that there is an improvement in phase margin and a significant reduction in the Q or quality factor between the two different designs, shunt and series compensation. Well, why do we care about Q? Well, in power integrity, Q is a ratio of the stored energy to power loss. So the smaller your Q, the less chance of oscillation, which means better stability in your overall PDN design. The VRM is part of the PDN, so by using a series compensation in combination with the optimal capacitor selection, the Q can be minimized to ensure better stability while allowing you to match your VRM output impedance to the desired target impedance of your load. As a caveat, we can tune the series and shunt compensation to be identical from an output impedance perspective, but that only applies in the nominal case of the error amplifier's transconductance. Remember, the series compensation removes the sensitivity to the transconductance tolerance. This is important when the transconductance of your VRM can vary by over 33%. Moving on to test case 2, which is the ISL 8026. Here again, we are emphasizing that by using a shunt compensation, your VRM transient response is sensitive to the error amplifier's transconductance variation. As shown by using a 5 amp step load with a 6.3 microsecond rise time, we see a significant difference up to 77% improvement when going from a shunt to a series compensation in the transient response. Further, we see that with the shunt compensation design from Intercell, we have less phase margin at 57 degrees in comparison to over 71 degrees of phase margin with the series compensation. Lastly, again, the series compensation has a 97% reduction in Q. Flat Z means better dynamic current response. So now let's look at test case 3. Here again, we're showing a large impedance peak in the VRM, which is the LM20143 from TI. That impedance peak is with the shunt compensation network, and that leads to a phase margin of 27 degrees. Now, by optimizing that output impedance with a series compensation network and optimizing output capacitors, we are able to achieve a phase margin greater than 71 degrees and significantly reduce our Q point in the system. In fact, we're able to reduce it by over 97%. As stated earlier, we could tune the series and shunt to be identical from an output impedance. However, that only applies to the nominal case of the error amplifier's transconductance. That means that the series compensation removes the sensitivity to the transconductance tolerances. Again, this is important when the transconductance of your VRM error amplifier can vary by over 33%. There's no way to mitigate that with a shunt compensation network design. So on to test case 4, again with the rad-tolerant VRM from TI. Here again, we're showing that we can design the VRM's output impedance to be completely flat using the series compensation to allow a better transient response by removing the sensitivity to the transconductance tolerance. Lastly, as shown again in test case 5, we can see that by using a series compensation network, we can design the VRM's output impedance to be completely flat. As we have shown already multiple times, this will ultimately equate to a better transient response from the VRM by removing the sensitivity to the transconductance tolerances in the error amplifier. So, as we've shown, there are immense benefits to designing your VRM with a series compensation versus with a shunt compensation network. This means VRM manufacturers need to provide designers with the flexibility to choose their compensation network topology. As a designer, you need to select VRMs with access to Vcomp outside of the package on the VRM and VRMs that do not have internal compensation. If they have internal compensation, make sure you can disable it. Remember, perfect regulation is a terrible thing because that means your impedance is 0 ohms. That's not possible. The takeaway here is to design your VRM to have a flat output impedance as part of your PDN in order to ensure the best overall dynamic current response. In summary, we showed that by using a series compensation network design with your VRM, you can achieve better stability, better transient response, and mitigate the sensitivity to transconductance variation in the error amplifier, while designing a flat output impedance that can be matched to the impedance of your load, where a flat VRM output impedance means better power delivery to your PDN. This concludes our presentation today. Thank you for attending and for your attention and time. Are there any questions?